welcome Shubham Dwivedi from University of Waterloo. So he will be speaking on deformation theory of nearly G2 manifolds. Okay. I think you can
Okay,
start.
so yeah. So first of all, I would like to thank the organizers for this great initiative and for giving me an opportunity to speak here. So I'm going to speak about deformation theory of nearly G2 manifolds. So G2 manifolds are manifolds with exceptional holonomy, and I'll explain what they are in a bit. So this is based on a joint work with Ravini Singhal, who is also a PhD student at University of Waterloo, and it's based on the paper with this archive listing. So let's start with a brief introduction to G2 manifolds, or manifolds with a G2 structure. So suppose I have a 7-dimensional smooth manifold, and throughout this whole talk, the dimension of the manifold will be 7, because that's where G2 structures make sense. So suppose I have a 7-dimensional smooth manifold, then a G2 structure on M is just a 3 form. It's a differential 3 form denoted by phi, which is non-degenerate. So for the purposes of this talk, all you need to know about phi being non-degenerate is that it induces a Riemannian metric and an orientation. So if I have a G2 structure on M, then this means that I have a non-degenerate 3 form phi, which means that it induces a Riemannian metric G phi and an orientation in a nonlinear way. So that's an important part, that phi induces the metric and an orientation in a highly nonlinear way. So once I have an orientation and a metric, I can define a Hodge star operator. So this is star, and I'm writing subscript phi to emphasize the fact that this star depends on what phi is. So once I have a Hodge star operator, I take the Hodge dual of phi. So I get a 4 form because I'm on a 7-dimensional manifold. And let's call this Hodge dual 4 form to be psi. So here is the definition of a nearly G2 manifold. So a manifold M with a G2 structure phi is a nearly G2 manifold if, first of all, phi is a G2 structure, and if you take the exterior derivative of phi, then you get 4 psi. So exterior derivative of phi is a 4 form, but it need not be a scalar multiple of the Hodge dual of phi itself. But I'm saying that if such is the case, then we call M as a nearly G2 manifold. And this 4 is, you can put any constant here. I'm just choosing 4 because that's what we do in the paper. And you can rescale the metric and then orientation to change this constant. So here's a remark. So the existence of a G2 structure on M is a purely topological phenomena. A G2 structure on M exists if and only if M is orientable and spinable, which is equivalent to the vanishing of the first and second Stiefel-Whitney classes. So W1M equal to 0 if and only if M is orientable, and W2M equal to 0 if and only if M is spinable. And by spinable, I mean that you can put a spin structure on the manifold. So here are 2 basic facts about nearly G2 manifolds. The first is that nearly G2 manifolds are always positive Einstein. So this means that the Ricci curvature of the underlying metric is a positive multiple of the metric itself. And since I mentioned on the last slide that a G2 structure or a nearly G2 structure on M exists if and only if M is orientable and spinable, this means you can put a spin structure. And once you have a spin structure, one can define what is known as a Dirac operator, which takes a spinner to a spinner. So Dirac operators are self-adjoint, elliptic, and so on and so forth. All right. So now suppose I have a 7-dimensional manifold with a G2 structure. So it's a common phenomena that whenever you have a G structure, where G is any Lie group, then the space of tensors, or in this case space of differential forms, they always decompose further according to the irreducible G representation. So in this case, the Lie group is the exceptional Lie group G2, and on the manifold M, there is a further decomposition of the space of differential forms according to the irreducible G2 representation. So these are given by following. So the space of differential 2 forms, omega 2M, decompose as omega 2 7, direct sum omega 2 14. So this 7 and 14 are pointwise dimensions of these spaces. And by Hodge star, this is isomorphic to omega 5. And similarly, omega 3M decomposes as omega 3 1, direct sum omega 3 7, direct sum omega 3 27. So again, these are pointwise dimensions, and by Hodge star, it's isomorphic to omega 4 m. So, and this decomposition is L2 in fact, it's pointwise orthogonal. So it's L2 orthogonal. So suppose I have an arbitrary 3 form or an arbitrary 2 form, then a priori that 3 form is a combination of these 3 components, and similarly a 2 form is a combination of these 2 components. But so that's where the importance of our first result comes into play. So what we proved is that suppose m phi psi, so remember psi is the Hodge dual of phi, is a complete nearly G2 manifold. So by complete, I mean that the underlying metric is complete. And suppose it's not isometric to the 7 sphere with the round metric, then every harmonic 3 form lies in omega 327. Equivalently, every harmonic 4 form lies in omega 427. And similarly, every harmonic 2 form lies in omega 214. Equivalently, every harmonic 5 form lies in omega 514. So if I have a harmonic 3 form, then from this decomposition, we see that a priori it can be a combination of any of these components. But what we proved is that if you have a nearly G2 manifold, then any harmonic 3 form must lie in the omega 327 component only. And similarly, every harmonic 2 form explicitly lies in omega 214. So this result completely characterizes the cohomology of any nearly G2 manifold which is not isometric to S7, because omega 1 and omega 6, they are already known by Poincare duality. So all we needed to know was information about omega 2 and omega 3. And by Hodge theory, harmonic forms basically describe the cohomology of the manifold. And this not isometric to S7 is not even a condition, because cohomology of S7 is already known. So we have describing everything else. So that's the first result of our paper. So now let's come to the deformation theory part of the talk. So suppose I have a nearly G2 structure, phi comma psi on our manifold, and what we want to do is we would like to see whether we can deform this given nearly G2 structure to a nearby nearly G2 structure. Let's call it phi tilde and psi tilde. So the way to address these problems is that one would like to look at the space of all nearly G2 structures under certain equivalences. And usually the case with geometric structure is that you look for equivalences. So you mod out by diffeomorphisms isotopic to the identity. So I am going to denote the group of diffeomorphisms isotopic to the identity by diff naught M. So here is a schematic diagram of how to approach this problem. So suppose P denotes the space of all G2 structures on M, and this mathfrak P, which is a pair phi comma psi. So it's not actually a pair. It's if you have phi, you can always get psi, but I'm just writing it as a pair. Suppose it's a point in this space capital P, and suppose it's a nearly G2 structure on M. So everything inside this green curve is the set of all G2 structures, and I have a point mathfrak P, which is a nearly G2 structure. And so this group diff naught M, which is again diffeomorphisms isotopic to the identity, it acts on this space P, because this phi is always diffeomorphism invariance. So let us denote by OP the orbit of this point P under the action of diff naught M. So this in this picture, this orbit is denoted by this red curve. So usually, like the general strategy for studying a deformation theory is to first prove what is known as a slice theorem. So a slice theorem basically says that you can find what is known as a slice, which is actually a submanifold of this space P, such that at every point you can get a complement, which is denoted by this curve C, to the tangent space of the orbit. So what we would like to do is we would like to say that this tangent space to the space capital P at the point small p can be written as TPOP, where this is the tangent space to the orbit, plus a complement. So we proved a slice theorem by explicitly finding a complement to the tangent space of the orbit. And then the way we proved this slice theorem and the previous theorem on cohomology of nearly G2 manifold was to first define a Dirac type operator and then use mapping properties of that. So once we have a slice theorem, we can describe or we can characterize infinitesimal deformations of a given nearly G2 structure. So this result, which I'm going to state now, was already proved by Alexandrov and Simmelman in 2012, but we gave a different proof of this using our methods. So suppose K denotes the space of Killing vector fields on M. So these are vector fields such that when you take the Lie derivative of the metric, it's 0. So the theorem says that suppose I have a 7-dimensional manifold which is complete, and suppose there is a nearly G2 structure, then the infinitesimal deformations of this nearly G2 structure are in one-to-one correspondence with pair x comma c naught, where x is a Killing vector field and c naught is a 3 form which lies in the omega 327 component, such that this c naught, when you take the Hodge Laplacian of c naught, this is 16 times c naught, and when you take the Hodge Laplacian of x, you get 12x. So this theorem completely characterizes all the infinitesimal deformations space of a given nearly G2 structure. It says that they are in one-to-one correspondence with a pair of Killing vector field and a 3 form which explicitly lies in the omega 327 component, such that they both are eigenvectors of the Hodge Laplacian operator with eigenvalue 16 and 12 respectively. So as I say here, that this theorem characterizes the first order deformation of a given nearly G2 structure. Now the goal of our paper was to see, can we describe higher order deformations by extending this further. So this is just infinitesimal deformation, and we wanted to see whether can we do second order or third order deformation. So to this end, let me make a definition to describe what second order deformations are. So suppose I have a given nearly G2 structure phi naught psi naught, then a second order deformation of phi naught psi naught in the direction of infinitesimal deformation C1 eta 1 is a pair C2 eta 2, where C2 is in omega 3 and eta 2 is in omega 4, such that when you look at the formal power series, phi is equal to phi naught plus epsilon C1 plus epsilon square by 2 C2, and psi equal to psi naught plus epsilon eta 1 plus epsilon square by 2 eta naught. So this is the formal power series in this parameter epsilon. Then this is a nearly G2 structure on the manifold up to order epsilon square. So what that means is that if I take d of phi, then it should be equal to 4 psi. So if that is the case, because a priori that might not be true, I'm just taking any arbitrary 3 form and 4 form. But if that is the case, then we say that phi naught psi naught has a second order deformation in this direction. So that does not always happen. In fact, the obstruction on a given first order deformation of the nearly G2 structure phi naught psi naught to be extended to second order is given by the following lemma. So if phi naught psi naught is a nearly G2 structure and I have a pair C comma eta, which is in omega 3 cross omega 4 exact, which is a first order deformation of phi naught C naught, then a pair is star alpha comma alpha, which is in omega 3 cross omega 4 exact, is a second order deformation if and only if the L2 inner product of d star alpha plus 4 star alpha with chi is 0, where chi is any co-closed 327 form, which is an eigenvector of the Hodge Laplacian with eigenvalue 16. So this lemma puts a very strong condition for an infinitesimal deformation to be integrated to second order. Because if there is a second order deformation, then this L2 inner product must vanish, and this should happen for any chi which is in omega 327, which are co-closed and eigenvector of the Hodge Laplacian. So that led us to the final theorem of our paper. So the nearly G2 structures on homogeneous manifolds are completely classified. So Alexandrov Simmelman in the same paper in 2012, they proved that apart from this L-of-Wallach spaces, the nearly G2 structure on rest of the homogeneous spaces are rigid. And on this allopholic space, which is given by SU3 cross SU2 mod out by SU2 cross U1, there is an infinitesimal deformation space, which is 8-dimensional. In fact, it is isomorphic to the Lie algebra of SU3. So a natural question arises that do the infinitesimal deformation of this nearly G2 structure on the allopholic space can be integrated to the second order, because we already have a characterization for such a thing to happen. So this is the theorem which we proved that that is not possible. So precisely the infinitesimal deformations of the homogeneous nearly G2 structure on the allopholic space SU3 cross SU2 modded by SU2 cross U1 are all obstructed to second and higher order. And then the way we proved this result was again to use a special Dirac type operator, which is same as for the previous result, and to explicitly use the representation theoretic aspect of this space of the allopholic space. So that would be all, and thanks a lot for your attention.
Thanks, Shubham. If there are any questions.
So, I mean, these nearly G2 manifolds are much easier to, are they much easier to construct than G2 manifolds? I mean, where, so I guess G2 is where this P has to be parallel, right?
Right, right.
So are the nearly G2 ones much easier to construct?
No, I don't think so. In fact, so like for torsion-free G2 manifolds, this is, so the equation is given by a nonlinear elliptic PDE. For nearly G2, it's again a nonlinear elliptic PDE, but I don't think so that they are like, if given a 7-dimensional manifold, one can describe criteria for like constructing those. For homogeneous, it's like easier because they have already been classified. But for arbitrary manifolds, I don't think it's that easy. In fact, there is a latest paper by Fabio Podesta, I guess, where he describes a one-parameter family of nearly G2 manifolds on R4 cross S3. So in the non-compact, so that's like sort of the first example, I guess, in this setting. But yeah, a priori, it's like not that easy.
I see, but I mean, are there conjecture? I mean, for instance, for G2, there's this Donaldson approach, right? Of
right,
you take a bundle over Calabi-Yau and then try to glue these things
right,
together to construct a G2, right?
Right,
So
right.
are there some conjectures for nearly G2?
Not that I know of. I mean, so like for example, in the torsion-free case, like the first construction was by Dominic Joyce, where he does the like Kummer construction. Then, as you said, like Donaldson gave this idea of having to asymptotically cylindrical Calabi-Yau and then glue them in a nice way. So that is known as the twisted connected sum construction. But for nearly G2, I don't know like any conjecture or any approach like this. In fact, it would be very interesting to like see if to come up with such a construction.
I see, but at least heuristically, I mean, do you think this should, something like this should hold, or I mean, one should possibly?
Yes, like so while we were doing this project, so we had to like go through what Dominic Joyce did for his Kummer construction, and so as I said, this like existence of nearly G2 structure is also an elliptic problem. The only difference is that in torsion-free case, you have an elliptic operator acting on a tensor equal to 0, whereas in this case, you might get an eigenvector, but it's still elliptic. So like one expects that like things should go through with the modifications. I certainly expect that, but
maybe a nice problem for you to try.
Yeah, exactly. yeah. That's
all right.
correct.
Yeah, thanks.
Yeah, no problem. Yeah.
You can thank the speaker maybe.
Yeah. Thank you.
Thank you.
Thanks, Shubham.
Yeah, thank you. Thanks a lot for attending.